So here we are talking about color theory. So color theory basically is color comes from light, and light is a type of energy. And this energy is described graphically along an electromagnetic spectrum. So energy moves three-dimensionally in an oscillating line. Basically, it moves similar to waves on a water. So the distance from the top of one wave to another, or the bottom of one wave to another, is known as the crest. And the distance from one crest to the next is described as a wavelength. So the entire span of visible light on the electromagnetic spectrum is actually very tiny, though, measuring only 300 nanometers. So from radio waves down to gamma waves, all of this spectrum is measuring only 300 nanometers. A nanometer is 1/1,000,000th of a millimeter. Now, the thing to note here, I'm not looking for you to know all the nuances and details of this. I just want you to get the general gist. You won't be quizzed on this part per se. But just note that the shorter the wavelength at the bottom here, the cooler the colors are, and the longer the wavelength from crest to crest, the warmer the colors are. And through here, you'll see the full spectrum of light. Now, we are pretty familiar with color theory as far as subtractive theory. What is subtractive color theory? That's perhaps what most of you are most used to, and that is where you have red, yellow, and blue, and you mix them all together and you get black. It's called subtractive because as you add them, they become black. Now, this diagram from a textbook, I don't know, it doesn't quite render the colors as well as I would like, so I just want to look at this maybe in Photoshop, because maybe here you'll see a little bit more about what you're used to. So notice here, if we mix yellow, and we're talking about paints and pigments and such, so if I mix yellow and red together, I'm going to get orange. This is grade school stuff we should be familiar with. If I mix yellow and blue together, we get green, and if I mix blue and red together, we get purple. You mix them all together, and you get black. Now, there's a problem with this in that this really isn't entirely true. So this is close. The yellow's right. These are actually not the primary colors. Yellow's a primary color. The actual primary colors in subtractive color theory is yellow, cyan, and magenta. Notice here, I'm going to look at magenta and cyan. So watch the magenta here. The old color theory, it was red, so kind of close to magenta. And notice the blue here. The new color theory, it's cyan. So it's kind of close. Now in practice, utilizing red, yellow, and blue as a primary colors, say in painting, it still works pretty well because of how close it is. But also consider that your basic printer doesn't have red, yellow, and blue inks to it. Well, it has yellow, but it doesn't have red and blue. Instead, it has cyan and magenta, the CMYK, cyan, magenta, yellow, and black. That's because these are the primary colors. Now, consider a primary color is defined as a color that cannot be created by mixing two other colors together. So let's have our mind blown. So here in this video, notice the color that's already laid down is magenta, and here we're going to add a little yellow. And to that yellow, we're going to add a little bit of magenta. Question is, what color does that make? And our mind is officially blown. This creates red. If red is a primary color, it cannot be created by mixing two other colors. But here we mixed magenta and yellow together, and it indeed created red. One more example. Here we've already laid cyan down on this board. Now we're going to mix cyan and magenta paint together. Question is, what color are you going to get? And sure enough, there is your former primary color of blue. So blue cannot be a primary color since it is created by mixing two other colors together. So again, this is kind of our new setup for subtractive color theory. Again, keep in mind, practice with like painting and such. Paints do have a slight different reaction, different kind of qualities that make them up, meaning the materials, different impurities. They can make each paint react differently, but in the basic theory of this all, cyan, magenta, and yellow are the primary colors in subtractive color theory. Now, we're actually not dealing with subtractive color theory when it comes to photography. Instead, we're dealing with the additive light color theory. So we need to switch our thinking here. We're not going to be mixing inks together. Instead, we are going to be mixing light together. So I think the best way to envision what I'm showing you here is the black background is just a black backdrop where no light is shining on it. So we're in a completely dark room. We do have 3 spotlights, however, in this dark room. We have a green spotlight, and so it's just shining green light on this black backdrop. We have a blue spotlight, so it's just shining blue light on this backdrop. And then we have a red spotlight, and that is just shining red light on that backdrop. Now notice what happens when the blue light and red light shine in the same spot. You then get magenta light. Similarly, whenever red light and green light are shining in the same spot, here they're overlapping, you get yellow light. And then when green light and blue light mix together, they shine in the same spot, you get cyan light. And when all of them are shining in the same spot together, in other words, you're mixing red, green, and blue light all together, they're all shining in the same spot, you get white light. This is why it's called additive, because as you add them together, you get white. Subtractive, you add them together to get black. So again, it's important to note we're dealing with light and not physical pigments or inks. Also, it's important to note that opposite of blue, I can see where red and green mix together. This is its complementary or contrasting color. The opposite contrasting color or complementary color to blue will be yellow. The opposite or contrasting color to green will be magenta. And then the opposite or contrasting color to red will be cyan. So this is something that you should have a decent grasp of, especially moving forward in photography, because as you start to adjust certain color aspects of a photograph, it is dealing with often primarily these primary and contrasting or complementary colors of light. So it is good to know blue and its complementary color, red and its complementary color, green and its complementary color. As a side note, perhaps it might be good to note that this is kind of opposite of how it was in subtractive. So notice how the primary colors, instead of red, green, and blue, are cyan, magenta, and yellow. So just a little side note there. Okay, so moving on, we are now looking at a Kelvin scale. So what is Kelvin? Kelvin is a different temperature scale. So we have Celsius, Fahrenheit, and we have Kelvin. Kelvin is most closely associated with the Celsius scale, which we're not terribly familiar with. And again, don't worry here, I'm not looking for you to memorize these numbers. I just want you to understand the general gist of this. Kelvin scale is basically the Celsius scale, except it starts at 0 degrees Kelvin, and that equals negative 273 degrees Celsius, ostensibly the coldest temperature that can be reached. So looking at this Kelvin scale, what we're dealing with is the color of light. And so we're not dealing with the color of an object so much as the color of light itself. So the way that this scale is based upon, so here we have a temperature of 1000 Kelvin, and we have a very reddish color to it, so a shorter wavelength. And the hotter and hotter the temperature, the longer the wavelength and the cooler the color. Now, this doesn't mean that if you have a blue light that is 10,000 Kelvin. This is kind of a slightly abstracted scale in that it's based upon a theoretical black box. And I'm not going to go into all the nuances and details of that, nor do I understand all those nuances and details just because I don't care to look into it that much. Of course, you're certainly welcome to yourself. But basically, this black box, as you heat it up, consider, like, let me step aside here for a second. Consider a campfire flame. So often it's going to be a reddish color. You know, notice at the end, your campfire is sizzling out. It's not as hot. You get those red embers, you know, in the wood. You know, but as it gets hotter and hotter, the flame can start to get a little red. We're used to yellow in there. That flame gets really hot and it starts to turn to a bluish color. And so it's similar to that in that this theoretical black box, as you warm it up on that Kelvin scale, it starts to, that heat from that energy starts to release light and a color of light. So the hotter this black box gets, the cooler the color of light is. So this is where this is basically derived from when we talk about using this Kelvin scale. Again, it's not the actual physical temperature of your light. It's just the color of light is equivalent to this theoretical black box being heated up itself and the theoretical color of light that it would emit. So again, notice that the lower the temperature towards the top here, the warmer the light, something like a candle here. And as we start to warm up the temperature, we start to get more of a yellow light, something closer to direct sun at noontime. And you warm that up more and more, we start to get a more bluish color. So here we have an overcast sky, or here at 10,000 Kelvin, we start to get something more in the shade. So that would mean that, if you're photographing during a regular sunny day and you get something in the shade, in addition to that picture, so most everything's in sunlight, but a little bit's in shade, that shaded area is going to look a little more cool than everything else. And that's just because of the color of light that we find in different lighting situations. So why is this important to you? It's important to you because every time you're photographing, our eye normally corrects for things to some extent or another. So if you're looking at everything by candlelight, it doesn't look as red as it perhaps actually is. Now, it still is going to look a little reddish, a little warm, and we can see that, but generally our mind kind of corrects for that. Well, the camera doesn't. It's not biased at all for that. It doesn't have a brain that just does this kind of auto corrections so much. So what happens is, in different lighting situations, we're going to get different overall colors of light. And as such, we have a white balance option on our cameras. Now, for the most part, most of you, if not all of you, have been using an automatic mode or a semi-automatic mode. And on that, it is calculating the white balance for you. And sometimes that can do really well. Other times you might need to kind of override that. So if you're not shooting in RAW, which ostensibly you're not shooting in RAW right now, and that's okay, whenever you shoot that image, you get a JPEG version, and if the white balance is really off, that's going to be really hard to kind of see. So this week's assignment is going to be dealing with this kind of color of light. And so we're going to change our white balance to see what these different settings do to the image and see what this color cast starts to have whenever we have these settings in a different fashion. So here, all 6 of these images are shot with the same white balance for the camera. And just notice that throughout the day, that the color of the overall building starts to change significantly. So it's not that every time at 6:30 a.m. you're going to get this color look to your image, and then at 7 a.m. you're going to get this color look. This isn't 100% specific to times a day, but there's a general gist to this. So certain lights can start to come in. This works best perhaps on a clear day. To give an example like this, because you start to introduce overcast light, you get a very different quality or color of light. And so this is kind of our goal of this assignment, is to start to shoot these different white balance settings just so you get a better idea and sense as to how this white balance is working within our image and how our camera can compensate for that.